Hello everyone, this is Yashu here and let us continue our discussion on uncertainty principle. In our previous video, we had a bit of introduction on uncertainty principle and we arrived at the statement of uncertainty principle. So in this video, let us study about the elementary derivation and we can see various forms of uncertainty relation and we can have more precise definition for uncertainties. So let us start off. Here, let us consider the wave packet and let the given length of that be delta x and n be the number of waves of mean wavelength lambda. So that we will have the equation delta x it is equals to n into lambda. So if we have another very close wavelength that is lambda plus delta lambda, then we will get delta x it is equals to n minus delta n into lambda plus delta lambda, because for very close wavelength lambda plus delta lambda the number of waves will be n minus delta n. So if we replace the value of delta x in equation number 1, then we will be getting n minus delta n into lambda plus delta lambda, which is equals to n into lambda. So now we can just multiply these two terms. So we will get n lambda plus n into delta lambda minus lambda into delta n minus delta n into delta lambda, which is equals to n lambda. Now you can see that n lambda is there on both the sides, so they will get cancelled. We will be having the terms n delta lambda minus lambda into delta n minus delta n into delta lambda, which is equals to 0. And we know that delta n into delta lambda is very small, so we can just ignore that term. So we will have n into delta lambda minus lambda into delta n, which is equals to 0. Now we can just transpose one of the term to the right hand side. So we will have n into delta lambda, which is equals to lambda into delta n. Now we can again transpose lambda terms to one side and n terms to the other side. Hence we will have delta lambda by lambda, which is equals to delta n by n. Now we have the de Broglie relation, that is p it is equals to h by lambda, and using this we can have delta p value, that is h by lambda square into delta lambda. And you should know one thing, that here we are trying to arrive at the mathematical form of uncertainty principle, that is delta x into delta p, which is greater than or equals to h. So from equation 1 we have the value of delta x, which is equals to n lambda, and now we need the value of delta p. So here we can just write delta p by p and we are substituting the values. So h and h will get cancelled, lambda will get cancelled with this lambda. So we will be left with delta lambda by lambda, which is equals to 1 by n. And therefore we will have the delta p value, which is equals to p by n, because here we are just transposing p to the right hand side. And now we have both delta x and delta p value from equation number 1 and equation number 2. Now we can just write it here, delta x into delta p, which is equals to n lambda into p by n, and you can see that n and n will get cancelled and we will be left with lambda p. And again we can use de Broglie relation, and here you can see that if we transpose lambda to the left hand side, then we will have lambda into p, which is equals to h. So we can just write here lambda p, which is equals to h, and therefore we arrived at the uncertainty relation, that is delta x into delta p, which is greater than or equals to h. And this relation is for one dimensional consideration, and for three dimensions we can get the following relations, that is delta x into delta px, which is greater than or equals to h, delta y into delta py, which is greater than or equals to h, and delta z into delta pz is greater than or equals to h. And now we can see the various forms of uncertainty relation. So here what we are doing is, we are just changing the pair of canonically conjugate variables. Earlier when we were discussing about the statement, we were talking about position and momentum. Here let us talk for energy and time. So these two are canonical conjugate variables. Therefore we can write uncertainty relation as delta E into delta T, which is greater than or equals to H. And as you all know, E is the energy and T is the time, and H is the Planck's constant. And if we again change the canonical conjugate variables as angular momentum and angular position, then we will have the uncertainty relation as delta L into delta phi, which is greater than or equals to H. And as you all know, L is the angular momentum and phi is the angular position. So we can go on writing the various uncertainty relations, but here let us just write the general form so that you can just substitute there. Here we can generally write the uncertainty relation as delta q into delta p, which is greater than or equals to h. Here q and p are the two canonical conjugate variables. And now let us see the most precise definition for uncertainties. That is, h bar will be included here, and you people might be confused between h and h bar while writing the uncertainty principle. So let us get a clarification here. Here we are arriving at the precise definition for uncertainties using RMS deviation, that is root mean square deviation. Here let us consider x to be the variable, so that the uncertainty delta x in x is defined by delta x whole square, which is equals to, here you can see this bracket symbol that denotes the mean values, which we call as expectation value. So expectation value of x minus expectation value of x into whole square. Here you have to see it in the form of a minus b whole square, so we can just expand it, and you can see here these brackets will be remaining as it is, and we are just expanding the inside terms. So it will be x square minus 2x into expectation value of x plus expectation value of x whole square. Again you can see here we can just apply this expectation value bracket to the terms inside. So it will be individual for each the terms, and it will be expectation value of x square minus 2 into expectation value of x into expectation value of x plus expectation value of x whole square. So here you can see that expectation value of x two times, that means they are getting multiplied, so it will be expectation value of x whole square. So you can see these two are like terms, so we will be having the final solution to be delta x whole square, which is equals to expectation value of x square minus expectation value of x whole square. So similarly we can get the uncertainty delta px in px, which is defined by delta px whole square, which is equals to expectation value of px square minus expectation value of px whole square. So by using these two we can arrive at the relation, that is delta x into delta px, which is greater than or equals to h bar by 2. And many people will write h bar, it is equals to h by 2 pi instead of h. And in consideration of the order of the value of the product, it is having any sequence, that means it doesn't make much difference, that's what I can say. So this is the most precise definition for uncertainties. So thank you so much, and let us continue the discussion on uncertainty principle using illustrations and applications in our coming videos.